We all know the feeling. You click a link, and instead of getting what you want, you are trapped staring at a spinning loading wheel. Then you switch to a different app, and it responds instantly, loading thousands of images and data points without a single hiccup. That difference in speed determines whether a user stays or abandons your product. To understand the architectural secret behind the websites that feel instantaneous, we are looking at Chapter 7 of Sriram Gopalan's book, Bridge the Gap. The core bottleneck of any application is its database. Imagine a massive 500-page Yellow Pages directory. If you want to order a pizza, you have to flip to P, find pizza, scan the page for your favorite restaurant, and read the number digit by digit. It works, but repeating that slow search for every single user request will quickly paralyze a system. Engineers solve this by introducing a cache. Think of a cache as programming that pizza place into button number 1 on your phone's speed dial. The system stores the answers to the most frequent requests in a tiny, rapid-access memory layer. When a user asks for the homepage, the application bypasses the massive database entirely and hands back the saved answer in milliseconds. Software speed is a deliberate structural choice. Engineers make applications fast by intentionally building a bypass around the system's primary source of truth. This diagram shows how that bypass functions. When a user makes a request and the data is already saved in the memory layer, it is called a cache hit. The system grabs the data and returns it to the user in a lightning-fast 2 milliseconds, functioning exactly like hitting button number 1 on your speed dial. But look at the top half of the chart. If the requested data is not in the memory layer, you trigger a cache miss. Now, the system has to perform the slow database search, return the data to the user, and then do the extra work of saving that new answer into the cache for next time. Because of those extra steps, a cache miss is actually slower than having no cache at all. This creates an immediate physical limitation. Your phone only has 9 speed dial buttons. Similarly, server memory is finite and highly expensive. When the cache is entirely full and a user requests a new piece of data that needs to be saved, the system has to delete something else to make room. This flowchart displays how engineers program the system to make those cuts, using eviction policies. The most common is LRU, or least recently used. It operates on a simple logic. If you have a speed dial button for a dentist you haven't called in a year, that is the safest number to delete to make room for a new one. But there are other methods. The system might use FIFO, first in, first out, which blindly deletes the absolute oldest saved number, regardless of how useful it is. Alternatively, it might use LFU, least frequently used. This policy keeps the number for your mom, who you call every day, but deletes the plumber, who you only called once, even if that one call was yesterday. Managing a high-speed application requires continuous automated triage. The system is constantly evaluating your user data to decide what is the least valuable to remember. There is a famous saying that cache invalidation is one of the hardest problems in computer science. Bypassing the database means you risk serving outdated information to your users, and in a live business environment, bad information is dangerous. This schematic illustrates the threat of stale data. If the pizza place changes its phone number, the primary database updates successfully, but the isolated cache is completely unaware of the change. It continues holding the old number. When you hit your speed dial, the application connects you to a stranger. To fix this, engineers implement a TTL, or time to live. This is a strict expiration timer attached to the cache data. Every 60 seconds, the cache is forced to self-destruct its memory and fetch a fresh, accurate copy from the database, ensuring the stored phone number is correct. Caching requires businesses to make a heavy, explicit trade-off. To achieve absolute speed, they must sacrifice perfect real-time accuracy and accept that some users will see slightly delayed data. That expiration timer is necessary, but it introduces a severe vulnerability. If a TTL expires at the exact wrong moment under heavy traffic, the tool designed to keep the system fast will be the exact mechanism that destroys it. This is known as the thundering herd problem. Imagine a cache expires at exactly noon. At 1 second past noon, 10,000 users request the homepage simultaneously. Every single user registers a cache miss. In a fraction of a millisecond, 10,000 simultaneous requests bypass the empty memory layer and slam directly into the database, cracking the infrastructure under the sudden weight. Engineers prevent this using cache locking. When that swarm of traffic hits the empty cache, the system gives a lock to user number 1. The other 9,999 users are forced to wait at the gate while that single user fetches the new data, safely repopulating the cache for everyone else. Hackers know how to exploit these mechanics. In a cache penetration attack, a malicious actor intentionally requests bogus data, like user ID -1. The cache checks for it, misses, and asks the database. The database also misses, returning a null result. Because the cache generally doesn't save null answers, the hacker can spam this exact request 1,000 times a second, tunneling right past the memory layer to melt the database. Without aggressive protective engineering, a cache acts as a magnifying glass for system vulnerabilities, rather than a shield against traffic. Serving stale data or dropping caches under load are lethal business risks. In 2012, Knight Capital Group lost hundreds of millions of dollars in a matter of minutes because of stale code and desynchronized systems routing bad trades to the market. Teams measure their success using a hit ratio, the percentage of time the cache actually holds the right answer. A cache with a 20% hit ratio isn't making the application faster. It is just expensive server memory masking a deeply flawed database structure. As Sriram Gopalan details in Bridge the Gap, speed requires complexity. It demands memory costs, eviction policies, and a tolerance for temporary inaccuracy. The next time an application feels slow, don't just ask to speed it up. Ask what data you are willing to cache, what data must remain perfectly accurate, and what that trade-off will cost. To dive deeper into the architecture driving our digital world, pick up a copy of Bridge the Gap and subscribe to the Explainer channel for more technical breakdowns.